Hi, my name is Garima Kocher. Thank you for joining us in our Zoom booth for this quick talk. The title on your agenda is called Geekfest, and my goal here is to talk about some HPC technology trends that we're seeing and what we're actually wanting to do about those. Once again, my name is Garima, and I'm a distinguished engineer at Dell working in the CTIO office. Jumping right in, here are some market and technology trends. I don't think any of these are going to be unusual to you. I believe Hyperion had a conversation earlier this morning as well. And but let's go through these really quickly. Systems are generating higher volumes of data, and that data needs to be analyzed. It needs to be analyzed faster with better fidelity. And faster performance for the analysis itself. And not only are we generating more and more data that we want to analyze, this data is being generated at multiple places in a distributed fashion. And we want to gather insights across all this data, which is in this distributed fashion. So think about what you want to do with data movement, how much you want to reduce it, how much data cleanup and analysis you want to do at the edge, for example. That's where all these factors come in. Along with this, systems are becoming increasingly complex, and folks are looking to simplify operations. Just listening to all the SC pre-announcements and the SC announcements this morning, it's overwhelming. How do you keep up with all the new stuff that's coming? How do you make sure that all these pieces work together? And how do you do that without deploying a huge staff of system administrators and IT operators just to keep things running and easier for the researchers using this infrastructure? We've seen over the years, and this is going to significantly continue, where automation and AI are driving significant changes in our IT architecture, and has touched HPC. HPC is a driving force behind it, and it's going to continue to influence what we do in high performance computing, high performance data analytics, and the whole AI deep learning and machine learning space. And of course, competition is increasing with Intel's GPU announcements and NVIDIA's CPU announcements and everything that's coming from the ARM vendors and RISC-V. But also vendors are driving to higher level and proprietary solution models. So where does that leave all the users of high performance computing? How much vendor lock-in is okay for efficiency or performance, but how much is too much before you're eliminating choices before you should? So with these trends in mind, let's double click into some more concrete things. So looking at the compute front, let's look at processor technology. We've already seen this underway, that we're seeing many cores on a single socket, but single threaded performance is remaining about the same. AMD had announcements last week. They've already announced 96 and 128 core CPUs, single socket, and this is the physical cores on the CPU. The graph shows us that over the generations, and one thing I love about this graph is that all this data is from the data that is measured data. All this data is from work that we've done at Dell in the HPC and AI Innovation Lab over the last over 10 years now. And the graph goes only as far back as Nihilum, which is that 2009 data point, but we have data even older than that, and for application performance as well. But just looking at the CPU itself, clock speed and memory bandwidth per core haven't really changed much in this time until Ice Lake in Milan in 2021. Cores per socket have shot up, and we know that a big piece of that is because of chiplet technology that AMD introduced with Naples and with Rome. Flops per clock has stayed about the same. So your performance improvements are coming from more cores on the socket, and your single threaded performance actually has remained about the same all these years. And with this chiplet architecture, you have complex NUMA that you have to deal with. There are latency challenges with local and remote IO, and there's this NUMA awareness needed, not just for memory, which HPC has done a really good job of dealing with all these years, but for network traffic as well as storage traffic as well. We know high bandwidth memory is coming to the CPU. We've had HBM on GPUs, but HBM is coming to the CPU with a future Xeon processor. So that should help with some amount of memory bandwidth. But how much is, something that that's the work that needs to be done, and which applications can take use of it. I already mentioned ARM and RISC-V architectures and products, lots of work and lots of new movements in that space as well. And all the stuff that's coming in 2022, 2023 and beyond, there's a step function increase in the power requirements. So as you push the limits to what your CPUs, and I'm talking about CPUs here, but your CPUs and GPUs can do, there's an increase in power requirements as well. And we all know that an increase in power requirements brings an associated cooling challenge. How do I balance density with power delivery and with providing adequate cooling to my infrastructure? So what's the work to be done here? All this new stuff that's coming, all these market trends and challenges, what's the actual impact to application performance? Dealing with chiplets, layers of NUMA, the compute capability of the cores, what's the impact to application performance? CPU high bandwidth memory, where can HBM be most useful? What data sets are going to fit? And what's the impact to my application performance? What's the software ecosystem readiness for ARM and now RISC-V as well? So we've been talking about ecosystem readiness for ARM for a while. And over the last year, we've seen a lot of interesting information coming out of from Fujitsu about the Fugaku supercomputer. But what do we do about software ecosystem readiness for the wide HPC market with ARM and with RISC-V? And once we have all these different technologies, what's the right technology and the right stack for different use cases? How do you pick? Are you going to pick based on, and there's multiple axes, right, on which to pick. There's, of course, always price. But since this is an engineering conversation and I'm an engineer, thankfully, I don't have to dwell on that one. But there's, of course, price, there's power and cooling requirements, and then there's the ecosystem readiness, the application piece of it, and then performance, of course. And the graphs on this, show existing measured data on the impact of, say, NUMA to I/O and the impact to process spinning, for example, on memory bandwidth. Simple things that need to be done so that that amazing new architecture and innovation that's coming, how do we best make use of it for our HPC and AI applications? On the GPU front, there's a lot of choices from our favorite partners, Intel, AMD, NVIDIA, but they all have diverse programming models. So we know about CUDA with NVIDIA, AMD has ROCm, and Intel's been talking about their One API. I already talked about increasing power requirements. And once you move away from these general purpose GPUs, there are many, many domain-specific accelerators for inference and training. Not just GPUs, but GPUs, FPGAs, custom ASICs, and of the order of hundreds of new domain-specific accelerators for inference. And again, this comes back to when you're designing systems for data analysis, where data is being generated, do you need a different sort of system design over there? Maybe it's on the edge. And what does that system design look like? And what sort of components do you need in that system design? The other thing that we're super excited about is this promise of cache coherence in the system. So cache coherence between CPUs and GPUs to start, all of that has already been announced. AMD's Infinity Fabric with CPU to GPU with the Frontier supercomputer. And this is the picture on the right is actually from Next Platform, and it's a little graphic of that system. You can see that the 4 AMD GPUs connected to a single AMD CPU here, there's cache coherence between them. And what does that mean in terms of access to larger memory capacities, fewer memory copies? How do you take advantage of all of this? NVIDIA's announced their Grace CPU and next generation GPU and a cache coherent link there as well. And we know about the CXL standard that's going to be coming out on our next generation CPUs. And CXL also has this promise of cache coherence. So what do we do with all this cache coherence, and how do we tune our applications for it? And then the other piece is that with all these new technologies, several of which are very proprietary in terms of their physical requirements, it's driving custom design requirements, right? It's no longer, okay, here's a server, or here's a rack scale architecture, and that's your component in it. What's the shape of that component? What are its power requirements, its cooling requirements? How does it plug into the data center? All of that is very different depending on those design choices that you make. And that leads to a very divergent portfolio, and then much more time spent in understanding how to deploy and manage and sustain these systems. So lots of work to be done there. So what does this mean? I already talked about the GPU programming models. Is this a concern for the community? We're very interested in hearing your feedback. What can we do here? One thing that, all NVIDIA, AMD, and Intel are doing, among others, is their own container repositories, and of course Dell's partnering with all of them on this. But what more can we do to make things easier for our users? I talked about cache coherence. How do we best use it? Which applications will benefit? How do we profile for it? How do we estimate performance? How do we program for it? And when things go wrong, like how do you debug and figure out what's going on to see if you're using that promise of cache coherence the best that you can for your applications? The other piece is, what's the best recipe for different classes of applications? Depending on which CPU and GPU combinations you're using, and how many GPUs you have to the CPU, and what additional acceleration features do you have? What are these trade-offs and optimizations? And is there a ready recipe I can use that allows me to get started quickly? And then I already talked about CXL. On the network front, InfiniBand remains the most popular, easy to use. Most of you all might have heard by now, OmniPath is back. There's a company called Cornelis Networks that came out of stealth about a year back. And, they have a full roadmap, and, the OmniPath architecture products with OmniPath. We've been doing a lot of work with Rocky and Ethernet at our end as well, with Intel and Broadcom. Rockport is another company that announced their product, and they have a distributed switchless architecture. The little graphic at the bottom is from a Rockport presentation that they did at a Dell HPC community meeting. And all of this is well and great when you're talking about point-to-point latency or network bandwidth, but what does it mean in practice? How do these different networks handle congestion? And are they easy to set up? Like if I really wanted to use it, the standard is InfiniBand, just plug it in, it works. Good management utilities, that's what we want to see. So the work that we're doing, active work going on for simple, easy to use configuration recipes for Rocky, for different applications and different system sizes, and then focus on network management tools, congestion management, congestion detection. And then there's this promise of DPUs, right? SmartNICs and data processing units. What's the difference between SmartNICs and data processing units? How much processing can you offload to that DPU, to that network card? And what additional functionality can you unlock? And where can you use them today? And what's the promise for the future? So that's work that we're actively looking at in the CTIO organization. I think I moved back, sorry about that. Moving on, GPU direct storage solutions are here. Dell's doing some work for this. And if you're interested in storage solutions, I really encourage you to reach out to any Dell colleague, including myself. There's a lot of stuff that we can share under NDA. It's not yet ready for this, open forum discussion, but work that we're doing on GPU direct solutions. The promise of DPUs as it applies to file systems, how can you make more efficient and highly performant file systems with DPUs? And then I've already talked a bunch about data cleanup at source and how you manage data movement. The little graphic on the right shows what that GPU direct storage is. Basically, you can see that, and it's from blocks and files. So it's a picture that's borrowed from that reference. Instead of having a GPU make a call to the CPU and then down to NVMe and back, the GPU can make a direct call to NVMe storage. And that's the GPU direct piece from NVIDIA. Data center considerations, right? I talked about a step function increase in power requirements. So you need to manage power densities, cooling requirements, weight requirements, and your high-end configurations if they demand liquid cooling. We saw the announcements come from TAC on how they've deployed a cluster with immersion cooling. What are we going to do as we move further? Or if liquid cooling may not be an option and power densities are a consideration, then with air cooling, do we no longer need super dense platforms? Because once you increase the height of a chassis, you have better air cooling capabilities there as well. And then with all these, and this is a theme that you'll see in the Hyperion projections as well. There's a push to as a service and different consumption models. Given the heterogeneity that we're seeing with the infrastructure, with the different workloads and the workload requirements, is this going to push us to different consumption models? Is this going to push us to deploying heterogeneous systems? And how do we make all of this easier? So if I'm talking about different consumption models with edge and on-prem, on my premise, a co-located data center or public cloud, or if I'm talking about multiple systems, even within my organization, what are the tools I need to allow applications to simply move to where they're best suited? How do I abstract this out for my users? What sort of portals and, what sort of intake do I provide so that everybody doesn't have to be an HPC systems expert to use the underlying infrastructure? And how do I balance this abstraction from that very low level tuning and best performance that we aim for, whether it's on the compute front, whether it's latency on the network front, or whether it's IO in terms of throughput or IOPS for storage. So some of the things that we're doing as we try to figure out what we do for these heterogeneous computing requirements is this Omnia project. So the Omnia project is a project from Dell, and you can see the GitHub link over there. It's a community-driven exercise for a framework for how you build high-performance systems. So very simply, it's a bunch of like Ansible scripts, recipes, so that you can stand up different systems on the same infrastructure, whether they're Slurm-based or whether they're Kubernetes-based. Depending on the workload, you can disaggregate and recompose your systems to serve those different workloads. So, completely community driven. Check out that GitHub piece and join the community. You can already see some logos there of folks who are using it, who've been giving us feedback, including that Google Cloud Platform logo over there. And there is a talk about Omnia in the booth tomorrow, I believe. So if you're interested in Omnia, come back and you'll hear more about it directly from the chief architect of Omnia. So trying to sum it up, what are our broad themes? Heterogeneous and composable architectures. Omnia is one piece of what you need from the software. There's a lot that you need from the hardware as well, but all of these need to come together. What do we do in terms of this orchestration and this open software ecosystem? Focus on storage and data management. I talked about different consumption models, and then design written recipes for different workloads, right? It's not so much like, oh, look at this, amazing store where you can get anything you need, but it's more about, what's your point of view on what's best fit given my requirements, my constraints, and my users and my environment. And I already talked about, everything that we're looking at in this space, whether it's, upcoming hardware technologies, new partners, software solutions, we're evaluating across all sorts of different axes, application readiness, the software ecosystem, performance, of course, ease of use, and different usage models. And I want to close with talking about our HPC community. SC is great, online SC not so much, but I'm delighted that we have this forum at least, and that we get a chance to talk to you. Dell has been running weekly 1-hour meetings on pre-announced topics as part of our HPC community meeting. We used to have 3 meetings a year, one in spring in Austin at the Dell headquarters, one at ISC in Europe, and one at SC. During this pandemic, we shifted that to weekly 1-hour meetings, and those topics are pre-announced. So if you're interested in the topic, you can register, get a Zoom link. It's very well kept on time, and the meetings are archived and recordings are available, right? So if you want to browse that website, dellhpc.org, and there's really active community participation each week. So even if it's a topic that you know nothing about, or if it's a topic that you're very well versed in, there's an active conversation going on. So I encourage you to check it out. The other piece I wanted to mention was HPC-NG, Next Generation of High Performance Computing. This is a group, not just Dell, but Dell and a lot of other folks in the industry on, what do we need to do for the modernization of HPC capabilities for the next generation of high performance computing, which includes enterprise HPC and convergence of HPC and AI. What do we need from our software tools, from our frameworks? The community charter was just announced and is open for feedback. There are multiple working groups. 4 initial working groups have been announced and are seeking members who are interested in this. And there are many future working groups that need to be stood up. So if you're interested in HPC-NG, check out hpcng.org as well. And that's the end of my presentation. I'd love to take questions if you have any, or any feedback or anything you want to talk about Dell, high performance computing, supercomputing, or just any topic.